Welcome back. We're at 4.1. We're going to talk about angles and their measures and how different ways to measure angles today. But we have Mrs. Cofield and Rex are here.
Hi, we're going to help out.
Rex is no longer screaming. He's been squeezed to death, literally.
I can't make him go anymore. He just has to wave.
There we go. All right. Well, let's go ahead and get started with 4.1. There are lots of ways to measure angles. We're going to measure them with degrees, with radians, with bearings. What else are we going to measure them in? Revolutions is on your screen.
There you go.
We're going to talk about degrees and radians mainly on this video and leave the other things for your worksheets in class and some activities, mainly because you'll figure them out rather easily. Okay? Degrees from geometry. An angle straight across here to here measures 180 degrees. All right? A circle all the way around measures
360 degrees.
360 degrees. All right. One full turn around the circle is 360 degrees. We also call that a revolution, okay? One trip around. Now, those are all familiar. You've seen them before. What we would like to talk about is radians, which you may or may not have seen before, depending on how much your Algebra 2 class did. If you came from FST, this should be rather familiar. But a radian is defined to be the angle at the center of the circle which spans an arc length, or subtends an arc length, equal to the radius of that circle. So let's say this radius was 1. This arc length, or the length around the circle, just that far, is also 1, if it would be 1 foot or 1 inch. And whatever angle we choose at the center of our circle to do that is called a radian. Make sense? Somewhat. Okay, let's try this. What we have basically is we have arc length is defining our angle. And so the arc length all the way around, the circle.
Isn't that just called circumference?
That is the circumference. That's what it's called. We call that circumference. And the formula for circumference is
2 pi r.
2 pi r. All right, and we just decided we're going to make our radius 1 because that's what we're going to do a lot in this chapter. So if r is equal to 1, the circumference turns out to be 2 pi. All right, now what does that get us? Well, that means that the arc length all the way around is measured to be 2 pi, and our arc length is defining our angle. So our angle, our central angle all the way around is going to be 2 pi radians, based on this definition.
So there's 2 pi radians in a circle.
All the way around, 2 pi.
Right. Okay.
How many degrees are in a circle?
360.
Which leads us to this idea that 2 pi is 360 degrees. And if I just divide both sides by 2, I'm going to say that pi radians is the same as 180 degrees.
Okay.
All right, so that straight angle is now going to be measured pi radians. Okay, now, a couple of little vocabulary words before we get going any further with this. Standard position. For angles, revolutions, radiant angles, pretty much everything except for bearings, we're going to have a standard position where the terminal side of the angle is measured, the initial side of the angle is the positive x-axis. What that means is our initial side is always going to start over here. We are then going to measure counterclockwise. For those of you with a digital clock, that means we go this way. And the terminal side of our angle will be wherever we stop here, and this will be our angle. So our standard position of our angle is going to put the vertex of the angle basically at the origin, initial side to the right of the x-axis, opening counterclockwise. All right, bearings will be different. Now, reference angles. We're going to spend a lot of time with reference angles, but basically a reference angle is the acute angle between the terminal side and the x-axis. It's always important you understand we go back to the x-axis. So now we're going to do some examples with reference angles and standard positions, hopefully to make it make more sense, okay? You're up.
Okay, so the first thing we need you to be able to do is to draw radian angles. And this is what we call thinking in radians. So when we see the radian angle pi over 2, we're going to need to put an angle into standard position. Okay, so we know that we're going to start on the positive x-axis. Now, just a minute ago, Mr. Leckie told you that in an entire circle, there are 2 pi radians, and visually what we're showing you is that in half a circle, in a straight angle, over here will be pi radians. Now, I'm going to teach you how to do fractions without really doing fractions. As soon as you see this as pi over 2, you're going to convert everything into halvesies. I'm going to make this 2 pi over 2, because that reduces back to 1 pi radian, which means this is going to be 4 pi over 2 radians. So now I have a circle that I can count in terms of 2 pi over 2. So if from here all the way across to there is 2 pi over 2, then from here to here would be 1 pi over 2. And that's going to create the angle that I need. So
You just took half of it?
I just took half of it.
That's easy.
I like this in red here. So pi over 2 is basically 90 degrees. Okay? Now, we talked reference angles just a second ago, and we need an acute angle. Well, if I try to get back to the x-axis, that's 90 degrees. So that's not an acute angle anymore. So this one doesn't have a reference angle. We'll deal with that later.
So
Okay?
anytime you're on the axes, you don't have a reference angle?
Correct.
Okay.
Correct. All right, let's talk with 11 pi over 6. Okay? Again, we're going to start with our axes. This was 0, and this was pi, but now I'm measuring in terms of sixes. So I'm going to have 6 pi over 6, which is really a pi. If I go all the way around, I'm going to have 12 pi over 6s. Because 6 times 2 is 12. Okay, so let's measure our middle pieces here. What's half of 6?
3.
So this would be 3 pi over 6. So now I know that each quarter of a turn is counting by 3. So I've got 3, 6, 9, and then 12. Now I've made it all the way around. Remember, it's pi over 6s. Okay, let's go back and look. We needed 11 pi over 6s. Well, that's clearly between 9 and 12, probably a little closer to the 12. So my angle will start here. It will go counterclockwise all the way around, and it will be at 11 pi over 6. Now, we can do a reference angle on this one because we ended right here.
That was our terminal side.
That was our terminal side, thank you. And we're going to get back up to the x-axis. If I was at 11 pi over 6, and my x-axis all the way around is labeled as 12 pi over 6, what reference angle would that be?
1 pi over 6.
1 pi over 6 from 11 to 12. I like to write that as theta ref. Okay? I don't know how Mr. Leckie likes it. Not rough, ref. All right, let's do a couple more examples. Again, this would be a good place to stop your video. Give them a try yourself. Okay, we're back. So, we have 4 pi over 3 this time. So this would be 0 and 3 pi over 3. If we go all the way around, we double 3 and we get 6 pi over 3. Now here's the problem. It looks to us like we have 2 pieces, but we have 3 chunks that we need to make. So you can either think about this as being 1 chunk, 2 chunk, 3 chunks, which confuses people, or what's half of 3?
1.5.
1.5. So this is 1.5 pi over 3.
I like that better.
I do too. So if we count by 1.5s now, 1.5, 3,
4.5.
4.5 would be next. Remember, this is 4.5 pi over 3. And then another 1.5 would make us 6. Okay, we need 4 pi over 3. So again, we're going to start with the positive x-axis, and I need to get to 4, which is going to be after 3.
But before
All the way
4.5.
around. But before 4.5. Obviously, it's closer to 4.5 than it is to 3.
Does it matter if mine thinks exactly in the right place?
It doesn't, but visually later on in the chapter, it's going to help if you can try to get it pretty close. If you know which axis it's closer to, that's going to help you. All right, so now when we go to do a reference angle, you don't just go to the closest axis, you go back to x. I was at 4, I got to get back to 3. That's this little angle right here. Again, how much is that?
Well, 4 minus 3 is 1. So
Beautiful.
Pi over 3.
So how about 1 pi over 3? Okay? All right, last example, 2.9.
Where's the pi?
Where's the 2.9 what?
Like, where's the beef?
2.9 radians. Okay, so this time when I do my circle,
You mean
instead...
that's not 2.9 degrees?
No. You know
Why
how I
not?
know it's not 2.9 degrees?
Why not?
Because there's no degree symbol.
There is now.
Which means if you don't put a degree symbol on something that is degrees, we're going to think it's radians. And you will find out by the time we finish this worksheet in class, radian degrees are very, very different. Okay? All right, we said that there were 2 pi radians in a circle. Well, what is that as a decimal? That's about 6.28. So let's just work in decimals. This would be 3.14 because that's pi. What's about half of 3.14?
1.57.
1.57. He's so smart. How do you know that? Okay, and I'm not even going to make him find the next answer because I need 2.9. So that's between 1.5 and 3.14. It's going to be closer to 3.14. Again, draw it in there. You can pretend that my angles are straight. That's what I do all the time. Okay, so if I was at 2.9 and I need to get to 3.14, my reference angle would be going the rest of the way around to my straight line. So what would that be?
Whatever 3.14
Oh, come on,
minus
Mr.
2.9
Leckie.
is.
What
How
is
about
it?
0.24.
0.24 radians. Okay, so that is our graphing. All right. If you have any questions, make sure you see us in class about that. Okay, there are times where we need to get from the radians to the degrees and vice versa. So if you think back to that circle that we were drawing and the straight angle, remember we said that there was 180 degrees in pi radians, okay? And that's the conversion we're going to use. So if we start off with 200 degrees, you want to think about where can I put some degrees to make them cancel?
This
I could put
reminds
them
me of
down
chemistry.
here. Yeah, it's called stoichiometry. I learned that word last year.
You just like using big words.
I can't spell it though. And pi radians. So these degrees will cancel with these degrees, and this 0 will cancel with that 0, and I just have to reduce 20 over 18. But really it's 20 pi over 18. Okay, we have that reduced?
That's 10 pi over 9.
That is 10 pi over 9. 10 pi over 9 radians. I don't have to write radians because I didn't put any units on there, and that's my answer. Okay, what if we need to go backwards? What if I have 7 pi over 8 radians? Now I'm going to show you a cool trick here. If you draw your stoichiometry thing right here, and this would be your radians, then it makes your 7 pi over 8 easier. Instead of 7/8, think of it as 7 over 8. Okay, what about radians? Well, we know that pi radians make up 180 degrees.
Why'd you put radians on the bottom this time?
Why did I put radians on the bottom? Because I wanted to cancel with the other radians.
Oh, so if they're on the top and the bottom, they cancel out?
Yep, one of each. Cancel, cancel. Look, our pi's cancel too. Cancel, cancel. Okay, so now I'm left with 7 times 180 divided by 8. I don't really want to do all that in my head. I know that 2 goes into 8, and I know that 2 goes into 180 because that's 90. I know that 2 goes into 4, and 2 goes into 90. So now all I have to do is 7 times 45 all over 2. Okay? So go ahead and give that a try. It'll be 22.5 times 7.
I got 157.5 degrees.
And 157.5 degrees is beautiful.
But I
Don't
just
forget the degrees.
7 times 180 divided by 8.
On your calculator?
Yes.
Cheater. All right, so why do we need to be able to convert back and forth? Okay, well, when we have you graph, we do not want you converting. Just go ahead and graph. But the next example Mr. Leck is going to show you, you're going to need to be able to convert. So we are ready for arc length.
Arc length. We talked about arc length, and besides, when we deal with calculus, this is a pre-calculus course, calculus doesn't use degrees, so you always want to be in radians. All right,
I
arc
like the
length.
pies anyway.
You like the
Pie
pies?
is good.
Pie, some pie is good.
Chocolate pie is good.
Rhubarb pie, not so good.
Not so good.
Okay. All right, let's
Is
go back.
rhubarb anything any good?
Let's go back to the circumference of our circle. We said it was arc length. Circumference was arc length all the way around. Well, if I go all the way around my circle, I've established that that central angle is 2 pi. So really what this is arc length is equal to the central angle times the radius. And we formalize this with this formula right here. It just says S for arc length equals the central angle times the radius. But 2 pi was in radians, so my theta, my angle, my central angle, has to be in radians. So S is arc length, theta is the angle measured in radians, or the center of the circle, R is the radius, and if I want to know what my arc length is, I just have to follow this formula. Now, let's take a look at this.
My students called it SOR.
SOR?
S-O-R. That's not really an O, but they like calling it SOR.
That works for me. SOR. Okay. Anyway, we have theta equals 5 pi over 6. Now, just for practice, let's try drawing this, shall we? 5 pi over 6 would have been, we start at 0, and this would have been 6 pi.
Yes?
Half of that would have been 3 pi over 6. So 4, 5, 6 would have been 4, 5. It would have been about here, right?
Yes.
So that would have been 5 pi over 6. Now what we're trying to do here is find, if the radius was 4 centimeters, we're trying to find the length of that arc if the radius happened to be 4 centimeters. That's what we're looking for, okay?
So the length of the distance around that part of the circle.
Yeah, if we could cut it off, lay it flat, and actually measure it, that is the arc length.
Got it.
Okay, so no picture necessary actually to do the problem. We just follow the formula, but it helps if you know what it means. All right, what is theta? It's given to me as 5 pi over 6. The radius is 4. I simply multiply them together. 5 pi over 6 times 4. 4 becomes 2, and 6 becomes a 3. So this is 10 pi over 3. And if you read the directions, which I didn't the first time I did this problem, it says express the answer in terms of pi. So I have 10 pi over 3. Now what are units of this measurement for arc length?
Well, this is a length, and the radius was measured as 4 centimeters. So would it just be centimeters?
It's absolutely centimeters.
Okay.
So we have 10 pi over 3 centimeters is the length of the arc of a 5 pi over 6 sector, if you will. Okay? Now, what's wrong with this second problem?
It's in degrees.
I've got degrees, but my angle has to be in
Radians.
radians. So I'm not allowed to use that. So I have to take 125 degrees, and I have to change it into radians. So we multiply that by,
Well, draw your little stoichiometry.
okay, we'll draw the little boxes. I give in. We're going to put 180 pi on the bottom, and or 180 degrees at the bottom and pi on the top, so that our degrees cancel.
5 goes into both of them.
All right, and what's it end up being?
It ends up being 25 pi over 36.
That's works for me. All right, so what is that? That was our theta, our new theta in terms of radians. So again, if we want to find the arc length,
We just timed that by radius.
we just soar. Is that what we're saying?
Soar.
S is equal to the angle measurement. It helps if it lines up better than that. I know how to use my smart board. The board is smart, the user, not so much. All right, 25 pi over 36 times 1.5 millimeters. Okay, so what is my arc length equal if I multiply all that out? Because I am not doing that by hand right now.
Well, we're going to leave it in pi, so it'll be 25 pi over 24 millimeters.
25 pi over 24. And on your calculator, you could cheat. You can multiply 25 times 1.5, divide by 36, and make your calculator turn it back into a fraction.
I turned the 1.5 into 3 halves and reduced.
Oh, look at you. All right.
Millimeters.
Millimeters. All right. Let's go from here.
When are we ever going to use this?
When are we going to use this? You're going to use it next class period.
Oh.
But other than that, here's the idea. Angular speed is how fast something is spinning.
I don't like to spin.
Okay, well, maybe we should stop spinning. All right. Linear speed is how fast it's moving. Now, we got a couple of examples in class that might come in handy when you figure out that when you change the tire size on your car, you actually end up speeding if you put on bigger tires, and your speedometer won't tell you that. So that might be something you might want to know. All right, so what we're going to do is go from angular speed to linear speed and back and forth, and really it's just like converting. And last time we had pi is 180 degrees. This whole idea of stoichiometry, we're really going to have to look up the spelling of that word. But it's just basically a conversion. Now, we're converting speeds, which are rates. So we want to start with a rate. If I have my example here, a turntable, which some of you probably don't even know what that is.
Define that.
How about a CD player?
Okay.
It's rotating at 50 revolutions per minute, okay? For those of you who don't know what a turntable is, find your parents, and some of you might need to find your grandparents. But a turntable rotates at 50 revolutions per minute. That is a rate. So we're going to start with that. Now, we want to change this into its speed in radians per second. Radians per second is how fast it's spinning in an angular measurement. So it's an angular speed, okay? So how are we going to do this? Well, we're simply going to do our stoichiometry boxes again, and we've got 50 revolutions per minute. Now that's 50 revolutions in 1 minute. You can put a 1 down there if you want to. I've got to change this into radians per second. All right, well, what's easiest, to change from revolutions to radians or minutes to seconds?
Minutes to seconds.
Everybody knows how many minutes are in a second. So what we're going to do is we're going to extend this, and we're going to say there are minutes up here and seconds down here so that my minutes cancel. Well, how many minutes are in a second?
There's aren't any, but there's 1 minute equal to 60 seconds.
1 minute has 60 seconds in it. That's easier than doing 1/60th of a minute
There
is
you
1
go.
second. How's that? Okay, now we've got our seconds like we want on the bottom. Now we got to get radians at the top. Now, this doesn't always work out right away, but for this problem, we would like radians on the top, and we want to get rid of revolutions over here. Do I know how many radians are in a revolution?
Well, a revolution is 1 circle, so we do know it's 2 pi.
Yeah, 1 revolution is just a trip around, so that's 2 pi radians. So we can literally just put that in here. 2 pi radians is 1 revolution.
So now revolutions will cancel.
Absolutely. Gone, gone. And I'm left with radians over seconds. Now, how do I get my final answer then?
We just multiply straight across this like fractions.
Yep,
Right?
just multiply, multiply, and then divide. So
So
we have 50 times 2 pi.
How about 100 pi?
That would be why we don't need the 5. 100 pi over, well, that's a 1, that's a 60, and that's a 1. I think I can handle that. That's 60 radians per second.
Should we reduce that?
We probably should.
Okay, how about 5 pi over 3?
That's awesome. And if any of you ever played Fallout, this rads per second thing, you'll know what I'm talking about. If you never did, don't worry about it.
I don't have a clue.
Okay. All right, that'll do it. This is not the same kind of rads that they're talking about in Fallout, by the way. Okay. I think that's going to do it for 4.1. See you in class?
That's it. We'll see you in class.
Rex is around here somewhere. We lost him.
You got bored and went away.
Bye-bye.
Bye.